We'll now analyze a spectrum with a lot of noise. We'll find the example here, number 2 in the list. So this is an iron sample, an oxidized iron sample. We see the oxygen peak here and the iron 2p peak here. We have other peaks here, a carbon peak and some other magnesium and other species here. We'll analyze the oxygen peak and the iron peak because they're easy to analyze. There are no interfering peaks like we have over here. So to do that, we first, because it's a fairly noisy spectrum, we will first reduce the noise. We can do that with the tools here in the menu in the Quasar software. Hit tools and hit the first one here, which is smooth and derivative by the Savetsky-Golay algorithm. You click the spectrum here and you have the smooth spectrum. You can put in the number of points that you use for the smoothing and the order of the polynomial you use in the fit. Usually you would be using 2 here and probably around 4 here. It starts at 2 here, there's a minimum. There's also already some noise reduction here, and when we increase this, we get more noise reduction. But we also start to distort the spectrum. If you look at the shape here of the peak, of the oxygen 1s peak, it's distorted when I go beyond 5. See a reduction here, and you see some funny peaks down here. We don't want that. You don't want to go too high. Probably in this case you would go to 4, which is a good compromise. You don't really distort the spectrum, but you get a significant reduction in the noise level. You can hit here to see the original, and you see there's a large reduction in the noise level without too much distortion of the peaks. You can also show the derivative here by clicking here, and you can find the position of the peaks from this. We'll be using the smooth here, and you can put in comment lines here to the file, or change the file name. We just use the default file name. So when I click here, I save this smooth spectrum. It gets the extension SMO for smooth. So this is a smooth version of that. We go back to the main menu, hit correct, because we now have to correct this for the analyzed transmission function. Now we more clearly see the iron peak here. So we hit transmission correct, and for hemispherical analyzers, which is practically always what we're using now for XPS analysis, this is a good approximation to assume that the analyzed transmission goes as the kinetic energy to the minus 0.7. So we just choose this default value, and we have the corrected spectrum here. So the next step is to isolate the peaks. Click here, and now you take the mouse and put in a window here, cut out the window, and I want to fit a line here in this range. So put in a background line here, put it out here. So I want to fit this line in this region out here, a little bit away from the peak. This is a satellite from the X-ray source. So I want to go a little bit to the right of that. So in this range here, you sort of have to imagine what would the spectrum look like if we didn't have the oxygen peak. It would go down following this trend here and keep following the line here if we didn't have the oxygen 1s peak. So when I subtract this line, I isolate the effect on the spectrum by the oxygen 1s peak alone. So I move down the line here, so it starts here, because we don't want to include this in the analysis. We just use this to get the slope of the line. And when I hit subtract line, it would cut the spectrum here at this point, and it will cut the spectrum either here or at the end of this line. So in this case, it will cut it here. So I do that, and this is now the oxygen 1s peak. So I just put that in, call this one oxygen 1s, hit save spectrum, and now we have the file up here. Next peak, click here, set next peak, and this is the iron 2p peak. So again, with the mouse, I put in the window here around that peak. I put in a line which I fit to this part here. So that'll be something like this. It's not too sensitive to whether I put it like this or like that. A little bit further down. You could do this as an exercise. This would show you what is the uncertainty in the analysis, and it's smaller than what you might think. But we remove the line again up to here and subtract the line, and this is the spectrum. So we save that. First we give it a name, Fe2p, Fe2p, and save spectrum, and this is now up here as well. Next step is to analyze these. Hit analyze here and hit the spectrum. We expect this to be a thick iron with something on top. So I just put in 3 nines here, 4 nines. So this is pure iron. It's clearly not that. Probably have some garbage on top, and you can see this is actually the case. To make the analysis, we need to put in the IMFP. We find the IMFP with the Quasys IMFP calculator. We can search for, now I have it already at iron 2p. We could search for the iron 2p. We'll do that by clicking here and say FeO. This will give us iron oxide here, and there are different oxides to choose from here. The values are not that different, and so we just take Fe2O3, and we need the energy of the peak. It's around 770, as you can see here. You can also get the number by looking up here. As I move the mouse here, this is the centroid, so it's about 770. I put the numbers in here, 770, and we have the value of 16.4. So I put that value in here, 16.4. The angle of emission, that's the normal emission in this case, so that's a 0 here. The cross section we use for analysis, we use the universal cross section. This is the default cross section that you would use in many cases. Whenever you have a transition metal or transition metal oxide, this is usually a very good approximation. There are other possibilities here for polymer, silicon dioxide, aluminum, and silicon. We just use the universal cross section. And that's it. We start the analysis now, and we see that it's clearly not pure iron, but we have something on top. How much do we have on top? About 40, maybe 45, something like 40 to 45 angstroms on top of the iron. So we know where the iron is. It's essentially from here and downwards, like 40 angstroms and downwards. So now we look at the oxygen peak. The oxygen peak is located at 950 eV. Put that in the calculator here, 950. And we have 19.2. Put that in here, 19.2. Now do the analysis. Now we expect the oxygen to be on top, so maybe I put in 0 here and 20, and I increase the thickness here. I can change the scale here so we can see what's going on. I change the thickness here so it starts to approach what we have there. That's the thickness of the layer, but we can clearly see it doesn't fit at all in this range, so we need to put something in here, and that's the contamination layer on top of the iron oxide. And I can fine adjust these values and get something like 30, 35, so like 80, 90, maybe 80, something like that. So now we know where the oxygen is. It goes from about 35 to 80 angstroms. And we know where the iron is. We found that was from from like 40 or 45, 40 angstroms to infinity. So this means that we have an iron oxide going from around 35 to 80 angstroms. We have something on top of this, which is carbon, mainly carbon, but other materials as well. There's probably also a small amount of oxygen in this layer, but not a whole lot. If there was a whole lot, we would see that here in the fit. We could also have used the optimized algorithm here. Let's try to illustrate that. If we take this some value here, which is clearly not perfect, we hit simplex here, move the lines here. This is where we want to fit the background from this to that energy. I hit background here and it finds the best fit. It's from like 35 to 75 angstroms, close to what we found from the visual analysis before.